All right, let's take a look at this one. So we got another motor and it's pulling on a box. Um, so what, let's take a look at it. If a motor exerts a certain force, determine the velocity of the crate when t equals 4. Coefficients of static and kinetic are blah, blah. Crates initially at rest. Okay. So just again, to make sure we all got it here, Newton's second law, it's a bridge. Okay. And kinematics on one side, forces on the other. So what's happening in this one? Well, in this one, it says determine the velocity of the crate. Okay. That means what we're looking for is going to be on this side. And notice it gives us all the information we need about forces. Okay. So we're going to start on the forces side of things and then we're going to move over to the other direction. Okay. So let's get going here. We know we've got the tension here and that's given to us. What that is, there's some friction pulling back here. And of course, there's a normal force and some weight. Okay, let's put all these on a free body diagram. Okay, super straightforward. All right, tension, normal, weight, friction. Okay, now on a test I'm going to want to see that. Okay, so don't take anything for granted. Remember, part of what you need to learn to do as an engineer is to communicate your ideas, to communicate your thought processes. All right, so your free body diagram is an integral part of that. Even if you might think you don't need it, do it. Okay, do it for the purposes of clear communication. Okay, so make a habit out of it. All right, that way you won't ever screw it up. Okay, so let's look at our y components here. Okay, MAY. All right, and we've got a normal force and some weight. And it's not spontaneously popping off of the sidewalk or falling through the floor or anything. So that term is 0. So our normal force is just mg, like so. Okay. And again, for the purposes of communication, it's good to go through that. All right, you need to at least make some kind of a statement saying, well, only N and mg are acting, therefore N has to equal mg. Don't just assume it and don't just force your audience to assume it. Okay, whoever's reading your paper or looking at your work needs to understand how you did each little piece. Okay. All right, now let's get to the x component. Start up here. MAX. There we go. And now we've got our tension minus our friction is MA. Okay. Now A is the key because remember we're eventually going to look for the velocity term. Okay, so that's why we got to get that A value. We know T, we know, well, what do we know about F? Well, we can come through here and we can go ahead and put mu mg, right? Just like that. In fact, we could even go a step further and say, well, our A is going to be T over M minus mu G. Well, that's kind of cool. Except the problem is we got two values for friction. All right. One, of course, is at rest, and one, of course, is if it's moving. So when it's at rest, that kinetic friction is 0.3. So, but how can we have an acceleration if it's at rest? You see what I'm saying? But on the other hand, if it's moving 0.2, it started at rest. So what do we do about that? Okay, so we got this weird kind of, it almost seems like a paradox. Okay, we needed to start moving, but it's not moving. Okay, so what do we use in here? Mu S or mu K? Well, what we have to do is we've got to think about what's happening with the force that's being applied at time equals 0. Okay, so at time equals 0, okay, it's going to be 10 times 0 squared plus 100. Okay, so we got 100 newtons right out of the gate. Boom. Okay, now that force then goes up rapidly, but we got 100 right out of the gate. So our question is, when it's supplying 100, are we able to move it or not? Okay, let's pretend for just a second that we couldn't move it. All right, we're pulling 100. It's not moving. Okay, but our force is going to go up with time. So maybe we can't move it right away, but after a few seconds or something, maybe then we got enough force to move it. Okay, so that could be the case. Or the case could be, instead of having to wait a few seconds, the case could be that 100's plenty. There it goes. Okay, so what we'll do is we're going to look at the static friction and figure out how much it resists. Okay, so can the static friction resist 100 newtons of force or not? All right, so our friction for static is going to be mu s, and remember this is actually less than or equal to there, mu s mg. Okay, so that's 0.3, and it's a 25 kilogram crate, and we got 9.81 meters per second squared. Okay, now when you work all that out, the static friction has to be less than or equal to 73.6, and that's newtons, of course. Okay, very nice. Okay, look. So the maximum that the friction can do is 73, but right out of the gate, boom, as soon as we start, we're pulling with 100. Okay, so this thing is moving immediately. Okay, it's moving immediately. All right, now you need to go through this kind of a process every time. Okay, don't just assume that it's going to work out like this, because let's suppose, for example, that they had written our force as maybe it's still 10t squared, but instead of plus 100, what if it's plus 50? Okay, if it's only plus 50, 50 would not be enough to overcome that. And so what we would have to do is we'd have to come in and say, okay, so at what point do we break that static friction? And so the way we figured that out is we would go 73.6 has to be equal to 10t squared plus 50. Now, that's going to enable us to find out the exact point in time at which it's going to be able to move. Okay, and that'll come into play in just a little bit. Okay, so just kind of hold on to that and know that for right now, we don't have to find that breakaway time, because the 100 newtons is plenty. It's boom, it's moving right out of the back. And so then we can come down here and say this is actually the static friction there. Okay. All right, so A, okay, and I'm going to put in what a T is. So I'm going to put 1 over m like this, and then 10t squared plus 100, and then minus mu sub s times g. Okay, so that's how I can get my acceleration. Acceleration is going to lead me to my velocity. Now this is a function of time. Okay, so the force is a function of time, so it's nonlinear, or it's not constant, and so that means Sam, Bumblebee, Optimus Prime, they're off the table. Off the table. They're not available to us. All right, but hey, no problem, because we know that A is a dv dt. Okay, and so we can take our dt around to the other side like that. Okay, then what we're going to do is then we'll integrate. Okay, dv, and then we're going to integrate. Okay, we've got a big term in here, 1 over m 10t squared plus 100 minus mu sub sg. And all that is with my dt. Okay, so it's kind of a big term in there. Okay, now we need to talk about limits. Okay, so when you're looking at the limits on your integration, remember, we want to start with what are the boundary conditions. Okay, so from where to where. Okay, and they got to give us something to work with on this. And what this tells us is the crate's initially at rest, so there's a 0 here, and at time 0. Okay, that means over here, then at the top of that one, we can put the final velocity. That's what we're interested in. And then we'll go ahead and put in 4 seconds right here, because that's our time of interest. Okay, then you just have to integrate that thing. All right, and that's super easy to do. So I'm not gonna go through that here. You guys can all work that out easy. Okay, just take your time. Plenty of opportunities for silly mistakes. Okay, just like that. Now, what I want to do before this video gets too long is talk about then, well, what do we do if we had this kind of situation up here? Okay, well, what that means is everything down to this point is totally fine. Okay, what we change is the initial time. Okay, so let's pretend that we find this, and let me call that t start. Okay, maybe t start turned out to be a half a second or something. Okay, we would put that t start right here, 0.5. Okay, so our integral that we found there, the dv equals stuff, that's valid for once the crate is moving. Okay, the scenario it gave us with the 100, it moved immediately. But if it didn't move immediately, we just have to adjust our time right down here. Otherwise, everything is the same. Okay, that's how you do that. All right. Okay, very good. Now, this is going to be the pattern in these sorts of things. Okay, we're going to be looking at free body diagrams and forces, and we're going to be looking at kinematics, and we're going to marry the two together to get our final answer. Okay, all right, get ready for another one.